First of all, good morning, everyone, and welcome to today's webinar on Ansys LS-DYNA, like we simulating the real world. I am Praveen Vahadni, and I am excited to take you through one of the most powerful and trusted solver, which is generally, we can say, globally used for high nonlinear dynamics problems and to solve real world engineering problems. Okay, so in the next hour, we will explore how LS-DYNA helps engineers like pushing towards the particular boundaries, whether it may be a crash worthiness, impact analysis, or blast events, forming simulations, okay, or advanced multiphysics, we can say multiphysics couplings. So we'll also discuss about the industries and we'll see about mainly how the LS-DYNA okay is capable or what are the key features and what are the practical applications. Okay, so this webinar will also give you an idea about uh, the uh, the holistic behavior or like say the holistic understanding of how ANSYS LS-DYNA supports various industries, okay, uh, in solving complex problems. So this session will be for the beginners, and by the end of the session, if you have any queries, any questions, you can definitely put into the chat. We'll try to support you in that, or we'll have a session Q&A session at the end. So start with the Ansys product portfolio. You can see here like Ansys has a broader portfolio and its presence is almost in almost every segment. Okay, so starting with the structural point of view, we have lot of like say tools like say Ansys Mechanical is there, Forming, Motion, Shell Log, Additive Solutions, Encode, Design Life, and Autodyne. So these all solutions are coming under structural part. Okay, and uh, LS-DYNA is the tool which we will be focusing today. Okay, and we'll discuss whether what capabilities of LS-DYNA will support for which particular domains. Okay, apart from that, you can see the presence of ANSYS in all the physics. It may be structural, fluid, electronics, semiconductors, acoustic, optics, photonics, okay, and even in the like say even in the uh, light segments or we can say glass segments, like say Zmax optics, okay, even into the optics, then even into the digital twin industry, AV simulation, mission engineering, safety analysis, and even with embedded softwares. We do have a database, material database, which has the information of almost all the OEM tested data of materials. Okay, and the most powerful things are like the Connect tool, which consists of three different uh, like say softwares, OptiSlang, Minerva, Model Center. So these are the tools which helps for the connectivity purpose. And even we talk about we can talk about Ansys Cloud also, but we'll have a separate webinars for all these separate tools. So today we'll be focusing on LS-DYNA only. Now, if you see this slide mainly, okay, it's like a market trend we can say. So this slide generally set the context for why advanced simulation tools are in high demand today. Okay, so as a product, if you see, uh, generally we want those products to become smarter, lighter, and more integrated. Okay, so traditional engineering methods can no longer keep up. That cannot be done, but still the industry is shifting towards the multiphysics, real-time simulation, and AI-driven automation. So we are also seeing an explosion in digital twins and clouds, or we can say HPC adaptations. So all of this means that simulation must be faster, more accurate, and more scalable than ever before. And that's exactly where LS-DYNA steps in. Now here we can see the outline for major engineering challenges. So most companies which are facing today. Okay, so as design becomes more complex, featuring advanced materials, multiple interactions, and strict performance requirements, so it becomes harder to predict real world behaviors. So slow simulation iterations further delay into design exploration and increase the time to market. And when huge models and massive, we can say, data sets, computing the resources often become a bottleneck. LS-DYNA helps to resolve all three challenges through high fidelity mode, fast explicit, and implicit solvers, and using HPC scalability. So this slide basically will give you an idea about uh, how LS-DYNA is considered as an industry benchmark. Okay, so LS-DYNA is renowned for handling extremely nonlinear, short duration dynamic events. It is preferred tool in automotive industry for crash. Okay, and has unmatched scalability on HPC. So the challenges which generally we have, okay, like say advanced, lightweights, and multifunctional, uh, which are generally predict we can't predict in real world performance. Okay, so those things we can predict easily with LS9. Now, what exactly these slides will give you an information about how LS-DYNA will address growing the product complexity. Okay, so modern products demands high safety, lighter weights, and more functional predictions. Okay, and those predictions generally we can say, those predictions uh, are cannot be done in a real world. So to get these scenarios, LS-DYNA engineers or LS-DYNA helps the engineers virtually to test the extreme conditions, large deformation, material failures, we can say, uh, multi-contact interactions, then we can say long before a physical prototype exists. So if you go before going with any prototypes, generally you can all do this activity virtually. So this reduces the cost and time to market while boosting design confidence. And next is the challenge of slow simulation cycle. So with tighter timelines, we can say, or competitive pressures on the companies, they cannot afford long simulation waits. So LS-DYNA accelerate this process and enables the virtual environment, okay, rapid virtual environment, and the early detections of failure, design weaknesses, and safety concerns will be considered for these stages. So the combination of scalable solvers and automated workflow makes this iteration faster and seamless. This challenge is becoming more relevant every year. Okay, so that is the computational and you can say the data management also. So if you see mainly uh, as model grows to the million of elements, including multiphysics, uh, LS-DYNA supports for parallelization and HPC support. Okay, which uses like a single machine can use thousand of cores, and definitely by doing that you can solve the simulations. Okay, sorry, solve the simulations, uh, which ensures the fast turnaround, better resource utilization, and deeper design exploration. So you can use this technique to uh, speed up the solution time. This is the same slide which follows or which supports the power through complexity. And this is generally we can say a success story from Volvo, which is a great example of LS-DYNA impacts when impacts comes into the picture. So basically Volvo also use LS-DYNA to execute more than 80,000 virtual crash simulations. So this seems to innovate adaptive safety systems and more closer to their vision of zero fatalities. And we can see virtual crash testing significantly reduce physical testing cost and accelerate the technical or we can say technology development. So as Volvo says, data is the new seat belt. Now let's talk about LS-DYNA. Now, when we talk about LS-DYNA, LS-DYNA has its own ecosystem. So this slide basically showcases the broader LS-DYNA environment. So LS-DYNA is not just a solver; it is an ecosystem. LS pre-post handles pre-processing and post-processing. LS opt basically it manages design optimization and robustness. LS task enables the shape topology. Okay, enables the shape and topology optimization, and together this tool creates an end-to-end workflow for solving the toughest engineering problems. Okay, so for example, LS-DYNA we can say it's a kind of a multi-physics solver with under one code tool which solves multiple problems starting from like say implicit to explicit. It comes across or has the capability to solve particle methods, chemistry, ICFD, CESE, okay, thermal. So all this uh, kind of simulation can be performed under LS-DYNA. So what makes LS-DYNA stand out? So it is a combination of decades of development. So huge element libraries are available. Hundreds of material models are available in LS-DYNA. Multiphysics solver and extreme parallel efficiency is there with LS-DYNA. So LS-DYNA has solution for structural mechanics, fluid, electromagnetics, you can say particle, like I said earlier about meshless methods also, and moreover we can see all within one environment. This slide will give you an idea about implicit versus explicit applications. Okay, so this slide generally clarifies uh, when to use implicit and when to use explicit. So explicit solver handle fast, high nonlinear events such as crash or impact. Implicit solver address static or slowly varying problems like structural stiffness or pre-stress. So LS-DYNA gives you both and even let you combine them seamlessly within a single workflow. If you see, this is the problem time magnitude from 1 year to 0.001 second, and this is the nonlinearity increasing towards the shorter duration time. So we can see the phenomena which comes under implicit methods such as creep, static dynamics, quasi-static, drop impacts, which is an intermediate problem. In some cases, it can come in implicit impact also. It can come under implicit and then it can come under explicit also. You can do this simulation both ways. But the simulations such as ballistic impacts, detonations, or hypervelocity impacts comes under explicit method. So if you see the real world problems here, what or which tool can deal with large complexities or large nonlinearities, instability issues, strong couple physics, robust simulation process, and including all these features. Okay, so if anyone mentions like what are the keywords like several deformations or material failures, buckling shock, so all these simulations essentially we can say if other solver struggles or fails to converge, LS-DYNA is the rescue tool to solve this kind of applications. These are you can see the LS-DYNA solutions. So these are the list of the solutions. These are like few solutions which are mentioned, but more related to the industry. Why Ansys LS-DYNA? So, like I said earlier also, so it's an uh, considered as a difficult in some cases historically because mainly we need to put some manual input decks, okay, and Ansys change this integration with LS-DYNA into Workbench. Now that is a important factor where engineers generally nowadays have an intuition or we can say intuitive interface which uh, solves or we can say which can carry out automatic meshing, reusable models, and they can standardize the workflow by using Workbench. So now LS-DYNA has uh, the compatibility with Workbench, where ANSYS Mechanical as the backend tool supports for pre-processing. Well, LS-DYNA also has the capability itself because it has its own pre-processing tool like LS Pre-Post, but Workbench interface has dramatically simplifies setups while offering the same solver power. The strength fields and the capabilities here you can see whether it is a drop, like I said earlier, misuse, contamination, failures, support equipment, LS-DYNA handles all the sectors like it serves automotive, manufacturing, defense, uh, biomechanics, consumer electronics, and civil engineering. Okay, so all sort of uh, simulations generally it can handle. It covers all these fields. Okay, so these fields are basically we can say the misuse fields. Okay, where failure fragmentations and large plasticity in mechanisms can be considered. Even with the manufacturing processes like machining, cutting, drawing, those can be done within LS-DYNA Workbench platform. So these are the fields which are covered by ANSYS LS-DYNA. Okay, so you can see under the civil engineering also you can consider a block proof like say uh, blast proofing, earthquake safety, tents. Okay, so those simulations can done under civil engineering. Okay, even with the defense you can see the projectiles, weapons, blast and penetrations, underwater shock analysis. So those will come under defense. So almost all fields are covered by LS-DYNA. And this is again the coupling, the multiphysics solver, which we have discussed earlier. And this is a strong coupling, multiphysics coupling, where we can see the thermal, like say solid mechanics, uh, data can be transferred, or we can say it can couple to each other. Okay, like SPH, solid mechanics, thermal, DM, ALE, solid mechanics, and thermal. So all these things has the uh, like coupling capabilities to carry out the multiphysics simulation. Okay, so generally we say as LS-DYNA as a one code tool. Okay, So LS-DYNA uh, includes all the solver of incompressible fluids, uh, ICFD, electromagnetic forming, particle-based airbags, blast modeling, discrete elements, meshless SPH, ALE for sloshing and material flow. Okay, so those things are there. Now coming to a kind of like say multiphysics capabilities, you can see, and in multiphysics generally, sorry, implicit capabilities. So when we talk about implicit, so implicit is typically a kind of a not a short duration process, but the time step generally which is taken in implicit is larger time steps as compared to explicit. In these simulation techniques, generally the element formulations, the materials, the constraints, and the loading conditions or the contacts, we can say, are moreover have a different scenario. It will be similar to explicit only, but the technique which follows for implicit is totally different because we have separate cards for implicit in LS-DYNA. Okay, but though as an implicit simulation, you can use this as a multiphysics analysis also where two-way structure or thermal, fluid, electromagnetic and their couplings can be done. Various simulations or various analysis types such as linear analysis, modal extractions, nonlinear analysis, combined explicit implicit analysis, and uh, this is mainly whatever the capabilities we have in MAPDL. Okay, so like Ansys mechanical. So all these capabilities are there in implicit, but it has more flexible methodology where you can switch from implicit to explicit during the solving process. Okay, so this supports mainly uh, when you can, if you want to transfer, okay, to if you want to transfer the implicit process to explicit, you can easily do this approach with LS-DYNA tool. So typical applications you can see dummy and HPM positioning, oil canning simulation, door sagging, rotor dynamics, okay, any a rooftop or we can say roof crash simulation. So these simulations we generally perform under implicit, okay, and the implicit is like say easily handled by LS-DYNA. Though LS-DYNA at the start uh, or it's robust in explicit dynamics, but implicit is also a feature available in LS-DYNA. So now you can see here multiphysics solver ICFD for incompressible fluids. Okay, so this will give you an idea about how ICFD okay is support for uh, the simulations which are generally performed by CFD solver. Okay, so automatic volume mesh generation includes the boundary layer mesh, turbulence flow for RANs. Okay, free surface flow, porous media flow, or it may be coupling to structural EM and thermal solvers. So this solver basically can be used over Fluent and CFX. But when a user needs to consider two-way coupling combining with large structural and nonlinearities, deformation, or when structural behavior is the focus of the simulation, then you can go over Fluent and other tools with LS-DYNA multiphysics, ICFD simulation. Electromagnetic solver is available, which enables or which solves the Maxwell equations using FEM and BEM in eddy current approximation. So this is suitable for the cases where propagation of electromagnetic wave in air or vacuum, we can say, can be considered And the main application are magnetic metal forming or welding, which generally uh, induce heating and battery abuse simulation. Okay, when we can use this when you have more larger structural deformation activity, then you can use over Maxwell. Now, this is basically a technique particles we can say where airbag, particle and particle blast applications can be used. So particle simulations are mainly used in the airbag, okay, or even for the blast applications for explosive particles. So to model a gas, okay, and it where you can inflate this gas in a particular time period, okay, in any volume. So you can use airbag particle, and similarly, if you want to perform an explosive particles, uh, we have particle blast simulation technique where you can model sand with DM approach, and you can also model explosive gas and air model, okay, air particle models uh, with this approach. Particles and DMs, the similarly like we have seen earlier about the particle method, but particles can be uh, uh, generally comes under we say like under DEM process only. So whether it is a agriculture industry or civil engineering, mineral processes, you can use DEM approach, okay, by using LS-DYNA. Okay, so LS-DYNA is all one and all solution for all these kind of problems. We do have a tool, similarly tool called Rocky DEM also, which is more robust in comparing or solving DEM solver capabilities, including the multiphysics application. But LS-DYNA also has the same capabilities, okay, for DEM, that is discrete element method. Meshless, generally we say SPH technique, smooth particle hydrodynamics, is generally the oldest meshless technique and which generally supports for the small fragmentation or droplets. So you can use this simulation with various for various applications. Okay. So even if you want to perform a sloshing behavior, okay. So this is also a kind of you can see this is obstacle and the contact force is continuously raised by the SPH or the transducers which are placed on the columns. So um, this simulations has its own like say when we are performing we generally follow certain element formulations, okay, so form 12 and form 15 and 16 which are we generally use for this kind of applications. Meshless, similarly when we talk about ALE, so ALE generally you can see it's generally we can say a kind of uh, multi-material Uralian mesh in a certain controlled way. So where you want to perform a turbulence models for ants, similarly like SPH, you can use ALE also method with LS-DYNA to perform certain applications for FSI, tank sloshing, material cutting, okay, and deep water explosions. Now coming to automotive safety or automotive crash. Um, in automotive sector, LS-DYNA is the global standard for occupant safety, air deployment, seatbelt behaviors, we can see, okay, and vehicle crash worthiness. So In this, you can see mainly uh, these are the different barriers. Okay, dummy models. Okay, impact dummy models, crash models, we can say, and the obstacles or the barriers. So all these things, like say MCB rigid, moving body, rigid, okay, PDB barriers. So these are already there within LS-DYNA database. Whenever we want to perform any simulations with respect to automotive safety industry, uh, you can download this particular models. Okay, so models are freely available to perform this kind of applications. So you can download this model directly from Ansys LS-DYNA website and use these models in your simulation. Airfold, like say airbag folding and deployment, is a kind of a process. This process is also, we can say, is being used in vehicle crash worthiness. So this process, we can understand the compression of the airbag with a specific and the deployment period. We can analyze it. So these are the model concepts starting from the earlier from 1990s to 2005. We do have now a robust techniques under simulation for crashworthiness. Earlier, the mesh, and we can see the computational power which was used was less. And today we can see we can use multiple component like multiple computers to analyze the entire vehicle. Okay, so we can use double precision, single precision techniques. Okay, SMP, okay, MPP techniques to discretize the model in uh, different um, computers to solve under one roof. So this is generally the today's reality of crashworthiness. So you have 10 to 15 million elements. The material failures, you can address the material failures, joint failures. You can use highly fully integrated element formulation, airbag, occupants. You can utilize directly. You can use the occupants inside. Seatbelt segments to segment contacts are there. Okay, and mainly you can see the computing power like 4 to 20 hours per simulations when you are using 224 CPUs per simulation. You can use MPP and hybrid LS-DYNA, or you can use on-premises hybrid cloud system. So the crash worthiness scenario from late 19 to 90 and today is totally different. Okay, so all these features are aggressively covered within the particular time frame. These are the safety regulations we can see. Okay, just to have a slide where you can get an idea about the regulations. So safety test regulations are there, and consumer NCAP. I think there's some issue. So you can see FMVSS 208 or all the standards from like European standards are there, or it may be US standards. So Australian different standards are there. So all the standards are covered under LS-DYNA. So if you have simulations for ECE regulation or FMVS or AIS, okay, so all simulation uh, can be done under LS-DYNA. It may be a whiplash analysis, it may be a pedestrian impact, it may be rollover, ejection and mitigation, rear impact, head impact, child safety. So all these are the regulations which generally uh, need a simulation. Okay, need an explicit simulation, and this where Now, in this case, generally LS-DYNA comes into the picture before because this kind of test generally required a huge investment. Okay, and this huge investment is not possible to carry out again and again. So to come up with a final prototype, generally we need to go with a tool where it supports you to perform this simulation virtually, and uh, with the help of this tool you will get a certain design output, and you can go with the physical testing. Like I said earlier about LS-DYNA, uh, it has HPC scalability also. So you can also see the uh, techniques, like it is widely used with MPI and OS platform. You can see the elapsed time here, the number of cores, okay, how many cores you can perform to compare between MPP and hybrid. So hybrid simulation, SMP and MPP extends scalability to thousands of cores. So you can go up to thousands of cores to solve this problem. Now coming to some important formulations within LS-DYNA, okay, which supports, uh, we can say, which are used in the industry. Mm. It may be a crash and safety, it may be any simulations. Uh, this features, okay, or this formulation, element formulation, is widely used for uh, for any deck preparation or any model preparation. So you can see solid elements, star section solids. Okay, so this is mainly a kind of a, you can say, advanced shell solid and thick shell formulations. So hundred of nonlinear material models with, we can say, uh, this one very basically like adaptive contacts. Okay, which we'll see in each one of the slides. But if you see solid elements, we generally define all this thing with star command. So to start with any keywords, okay, in LS-DYNA, generally we need to use star like in asterisk, like say star section underscore solid. So section is basically a kind of a card, okay, that is a control card, and solid is the it defines what sort of formulation or what sort of element it is. Okay, so section, what will be the section and what will be the element type. So that generally defines in LS-DYNA keyword card. So mostly if you use for bumpers or dummies or engine block transmissions, we generally use hourglass type 6. Hourglass is generally recommended for solid elements in some of the cases because zero mode energy is developed. So formulation 0 is mostly for foam, formulation 0 for rubber, formulation 1 for other applications. In the same case, when we go with section cells, so these are recommended for crash industries, okay, and also can be used in various other uh, like say simulation techniques. So shell elements, generally you can, for almost most of the parts, generally we use element formulation 16 uh, by using our glass type 8, because this formulation 16, okay, it's a fully integrated element, okay, and this supports, or we can say it has a minimum hourglass, or we can say no hourglass effect in that. But most of the cases for other elements also we can use star hourglass as as a card, okay, where it minimizes the hourglass effect. So hourglass is generally, we can say, a kind of a zero mode energy which is developed within the elements, which will not show you any sort of high deformation, or we can say uh, it will show you high deformation without no stresses developed in it. Okay, so it will be just a change in the shape of the elements, and it will take a shape of hourglass. So uh, formulation 9 is used for member membrane elements, which is mainly used for airbag and seat belts. So these formulations are very important for generic formulations. Like when we create any model, we can use formulation 2 also. It is under integrated element, but element formulation 16 is fast and it avoids hourglass effect. So element formulation 16 is recommended in most of the cases. Thick shell elements, we can say section T shells. It can be used for composite materials with different materials at each integration points. I will show you where to how we can see these cards also. Okay, so we can see. I will just give you a short walkthrough through LSP post also. So all the sort of composite materials with different materials at each integration point, you can use thick shell elements. Thick shells are more accurate than four noded shells. Okay, and if you see the thickness to the radius of the curvature of the part is being modeled with which exceeds generally zero point 0.1. So formulation from 5 or 7 is generally recommended to go with thick shell elements. So before going with any creation with any parts in LS-DYNA, generally uh, we need a part. Okay, so any part will have that is star part will have. Okay, that part will consider or will have its ID, part ID. Okay, then it will have the section ID, SID, that is the section which we are going to define. Okay, and the material ID. So what we have to do when we create any parts, okay, so these are the important inputs we need to define, and section ID, or we can say section, is nothing but it will tell you how the element look like. Okay, whether it is solid elements, whether it is shell elements, whether it is a beam element. Okay, so it will tell you about those things. And this ID, the ID which is created for this particular section shell, need to be defined in the part, that is star part. So we'll see those things in our detailed uh, learning of LS-DYNA. But today we are just going to uh, focus only on the overview part. Okay, we'll have another round of webinars where we'll cover uh, in detail study of, like say, how LS-DYNA, how to start with LS-DYNA, and what are the control cards, when to use which control cards. Now, similarly, like I said about for a part, it consists of mainly uh, it has a certain, like say, mm, material. So each any component uh, when we are defining in LS-DYNA or any other tools also, it generally needs this information. That is the property and the material property, the physical property, like how the geometry it is, like whether the it is what type of material, what type of element type it is, and what is the material which is being used for solving. Okay, whether it is steel or aluminium or whether it is a rubber material. So LS-DYNA has its own material library and material models available, starting from MAT 0, MAT 1, okay, to up to like say MAT 200 plus. So now when we to see each material, okay, each material has the name given like say MAT 24, okay, MAT 181, MAT 1. Okay, so mat one is generally elastic material, which is a generic material available in almost all material libraries, like all softwares, all different softwares. But when you see about mat piecewise linear plasticity, okay, it is a material which models plasticity. Okay, where you can model the plasticity with stress rate tabular curves. Okay, and with the help of stress strain data, okay, this is a stress and plastic strain, so you just need to have the true stress strain curve data Based on that, you need to identify the plastic region, and those plastic region you need to define in MAT24. The same way we have MAT 181, which is generally recommended for rubber. So no parameter fitting, you generally need the direct input of curve. Application examples includes additive and air impactor skins. So these are like, definitely we can say, kind of a simulation material where uh, the rubber is recommended. So MAT 181, uh, this is developed to capture the thermoplastic effects, tension, compression, incompression, and compression only or not in tension. So those things for the material is crucial. Okay, so to carry out this kind of simulation, this type of material inputs, you need to use MAT 181, where you can see or define separate compression, shear, and biaxial tension, stress and curves, as well as you can define the tension table. So what type of material is needed for you? You can visit material selector, this Dynamite uh, website. Okay, so I will show you. If you directly search this thing also, lstc.com. Now previously it was LSTC, but you can easily look for Dynamax. You just need to go to Google. You can search for Ansys materials. So here in Ansys LS-DYNA, you can see material vector. You can search directly also. And this is Ansys LS-DYNA dot materials. And in this, basically, you can look for any element, what whether it is a solid element, which supports which element, which materials. You can look for the family, whether it is a metal, composite, plastic, adhesive, rubber, foam, glass. So you just need to select those things and look for that general material. Okay. If you have a specific failures also, damage, equation of state. Okay. So you just need to search for that one, and it will sort out the materials for you, material model for you. Okay. So that much flexibility of feature is available with LS-DYNA to check within these things. If you are using spot whales or spot whale, generally this any family we need to select, and it will show you the match spot whale option. So when you click on it, it will redirect you to the MAT 100 theory, and it will tell you about uh, what this material model is. Okay, what this material model is and what sort of sections you can define. Okay, so this is the model for spot wells, how the spot well will behave, whether it will behave in a rigid form or deformable form, what inputs you need to define. So those things generally, what will be the damage failures. So all this study for the material one, you can do it with uh, Dynamat. Now, when we talk about popular contacts, okay, so contact in LS-DYNA, we have a wide variety of contacts, starting from node to surface, line to surface, edge to edge contacts, okay, going with surface to surface, or single surface contacts. Single surface means having the self contacts, automatic general purpose contacts, which is more robust as compared to single surface also. But single surface is more faster as compared to automatic, because automatic contact uses the edge to edge contact technique also. So it depends like what sort of contacts you are following, but there are several contact algorithms. Uh, the two ways to distinguish, you can see the method of searching for penetration method. Okay, generally we say as a penalty method. Okay, and three penetration search methods are being used: node to segment method, segment based contacts, mortar contacts. So mortar contacts are ideally used with the implicit approach. It is also one of the, like say, uh, these contacts are very much robust because it finds the slave master pair of which the master segment is in the shadow of slave segment. So it is generally recommended in implicit approach. Segment based contacts are like for each surface or each element, uh, the software creates a segment. Okay, and that segment is used in the contact. It uses a kind of a pinball technique uh, to search for the nearby nodes. Okay, so that is generally comes under segment based. And node to segment based method, generally we can say orientation doesn't matter because you have a single node and surface, and it automatically searches the method or searches the different contact surface. Compared to that, techniques for contacts, we can use tied contacts. Tied contacts are nothing but a kind of a bonded contact, we can say, or glue contact, but it do has the separate features available where you can use a tie break option, where at a certain time period after crossing a certain limit the contact can break. Okay, so the force nodes and the mass of each slave nodes is distributed to the master node, and which generally containing the contact points. The acceleration of the master surface is thereby computed, and you can see the acceleration of nodes generally interpolate for the master segments in tied contacts. Penalty contact, like I said earlier, it has three techniques where soft zero, soft one, and soft two is being used. Soft zero is used where generally the stiffness, the master stiffness, comes into the picture. Soft one is used for the contact between materials of very different stiffnesses, okay, which generally gives you a simulation stability. If, for example, one of your component is rubber material and the other component is steel material, so you can use soft one. Soft two is mainly depends upon the stiffness again, where the SFS or SFN, that is scale factor for slave surface. Okay, those are being considered in the simulations. So we can have a detailed sessions in our upcoming webinars where we'll deep dive into the contact techniques also. Popular connections which are used, uh, like you can see deformable spot rails, detachable fasteners, initial strays, that is preloading bolts, we say preloads or bolt pretension generally. Then non-detachable fasteners, which are adhesives, cohesive material family is been used for this one, like star, mat, cohesive. So all these popular connections are there in LS-DYNA as compared to other tools. If you see, LS-DYNA has moves element methodologies and materials, where when we talk about creating the seat belts or sensors, okay, or pulleys. So these are like the supporting tools and features you can see. Like I told you about the calibrated human dummy, barrier, models, and tires. Even we have tires also in LS-DYNA. So different tire models are available. If you need a tire model to analyze like how the tire model has been created, you can visit Ansys website and download this material models. So the options you can see in LS-DYNA like retractor, pretensions, generally we say slip rings, shoulder belts. You can create these things in LS-DYNA, LS pre-post. Okay, so if you want to create a slip ring, if you want to create the lap belts, the fitments of the belts, generally we can do easily in LS-DYNA or dummy positioning. These are generally dummies. So when we do a position the dummies, on the seats, you can use this. Now, this is not limited actually. So, when you have an approach where you want to perform a pulley application, okay. So, if you have a pulley application approach, at that time you can use slip rings. So, slip ring is a pulley. Okay, it is not used in only in the automotive industry. So, if you have an object or want to carry out a pulley application, okay, where you want to check the strength of the rope also, so you can use slip ring. Okay. So LS-DYNA, you can see good fit applications, helmet designs, okay, or it may be a PET bottle impact, drop test, consumer products. You can see mainly uh, rapid sealing process, flexible tube, and incompressible liquids, drop test of PCB. Okay, with BGA, you can see diaper folding. So these are like almost the different applications. Crimping approach, rolling, forming basically, hard forming with lancing, rivet piercing, spinning forming. Okay, so this when you see this application, these are very we can say uh, very complex applications. Okay, and these complex applications are easily handled by LS-DYNA. You can see impact scenarios. Okay, whether it is a glass, you can see here. This is a glass scenario where human head is impacting on the glass or monitor. So you can easily uh, perform this glass fragmentation simulation also. Cell phone drop, or it may be impact cracks. Okay, so all these things we can perform. Under civil engineering also, you can see structural collapse. Okay, how the structure is going to collapse. So how the structure is going to feel at a particular area. Tank sloshing simulation can be done. Nuclear seismic simulation. Okay, so under civil engineering, we can do this kind of simulations. Like we have seen about automotive safety and reliability also. So if you have a batteries also, currently we know battery impact. Generally, we can say battery uh, simulations. Okay, the internal short circuits which are developed in the batteries after the impact. So those simulations we can perform with LS-DYNA. Okay, the thermal runaway of the battery, which are generally used in electrical vehicles. Okay, so those things we can perform here. Okay, and mainly if you see the like if you want to analyze the temperature plus current density. Okay, so you just need to go with multi-physics solvers, but you can definitely solve this application with help of LS-DYNA. For batteries, generally we have a separate approach. Uh, how to create those things we can have in a separate sessions with our webinar series. Biomedical applications, if you see heart modeling, maybe a balloon inflation in artery, okay, endovascular surgical process, where the stent is moving, okay. So all these things generally we can do with LS-DYNA. So these are all the tissues we can say, the muscle modeling, the vein modeling, okay, the material which is being used in this. You can see the flexibility. Okay, so heart modeling is there. This is mainly we can say electro physiology plus mechanics plus flow. Okay, and balloon inflation in the artery. So you can model arteries as well. So the material which generally so LS-DYNA has the capability, or we can say the material modeling technique, where you can model even the arteries also. In aerospace, uh, LS-DYNA has a strong presence. Okay, so these are like few simulations which are performed by our partners, SPH, Bird Strikes, or like Ansys partners. You say turbomachinery applications also. If you see FSI techniques, gear sloshing simulations, hammer mill threads, so pressure relief valves with FSI particle method and structure. So you can do this thing with LS-DYNA. So mainly when you want to perform a failures, okay, within the model structural failures with high impact simulations or any sort of multi-physics application, you can use LS-DYNA as a tool. These are aerospace applications, the bird strike or the drone strike, drone hitting, drone impact, bird strike. Okay, again this is drone hitting. So in aerospace industry, these are like the impact simulation. Uh, Moreover, to write, if you want to perform a flight uh, simulation also of like say of drones and all, so those simulations also we can perform with LSTM. Defense, like say survivability and ballistic. So you can perform internal ballistic, external, in the air, thermal ballistic, wherever the target has been defined. Okay, and survivability, like say post impact simulations, you can check. So these are mine detonation simulations. Okay, mine blast, safety carrier crashes, and perform with LS-DYNA. In these different segments also, if you want to perform a small arm simulations, blood penetrations, okay, and it may be like hard targets. So those sort of hard target simulations, composite formatted or computer, like say composite, uh, the materials which are generally used for safeties. Okay, so to check those composite failures also, we can create those composite layer of modeling. Okay, this is not a composite modeling, but generally I'm just telling you about if you want to perform an impact on a, or a ballistic impact on a composite materials, you can do it. These are mainly on the soils or on in a water. Those kind of simulations we can perform. These are multi-stage weapon system. So first the small, then this larger uh, bullet is transferred. Okay, so this is multi-stage weapon system. The small bullet is guiding the larger one and it is going to penetrate. This is a similar way we can see for barrier, so for barrels also. Okay. And then we can shape charge after an impact. Okay, so those simulations are easily done. Underwater blast. And even if you want to see a rail gun, if this is the real scenario and the same way how the rail gun is been behaving, sliding contact is defined between the rails and the projectiles. So these are like the B field, rail, projectile, EM force. So current density has been defined, and you can see how it works. Just a second. This animation is not working. It's working this way. It's for the rail guns. Multi-physics applications, like we have seen, wall impact, battery pack, current density, which we have seen, fuel tank integrity after an impact, coupling with DEM to simulate mud or snow depositions, hydroplaning with flexible tires, wedding simulations. So these simulations we can do. And apart from that, you can see if you want to learn most of the tools, okay, we have Ansys LS-DYNA as a tool, uh, Ansys Learning Hub, which has almost all the tools material available for training and all. Okay, so coming to this thing, I will just walk through a short demo. Okay, we'll see both the things. If you want to go with LS post, generally I will show you about first how we can use LS-DYNA in Workbench mainly. Okay, so this will give you an idea about like how the LS-DYNA is now integrated with Workbench, and uh, this in this session generally, or we can say in this demo, you'll just see the drop test of a circuit board. Okay, using Ansys LS-DYNA, where nonlinear dynamic structure simulation software, which is Ansys LS-DYNA Workbench, where the procedure is to, we can see, to open the Workbench to check the unit system and all. So this is the interface of LS, we can see a Workbench. And under Workbench, if you see the toolboxes, we have LS-DYNA here. So if you drag and drop LS-DYNA, so you have different steps, like say starting with engineering data. So under engineering data, if you see, you have this information available, okay, for materials. But under this, generally, if you see physical property or linear elastic properties are there, you can use few of the materials, like say linear elastic materials, which in Workbench automatically transfer the material type to mat1, but we do have separate materials available. Okay, if you see here, we have uh, LS-DYNA materials available. Okay, so the materials which are generally used in LS-DYNA, okay, are available here, and the materials for equation of state or additional materials, damage, or you can see EM materials, electromagnetic materials. So those materials, almost all the materials are there. And if you want to go with the battery, so you can see battery, kind of a battery material properties which need to be defined are already there in this case here. So you can create a material directly. You can just write uh, uh, type material name, like say any mat. If I type here, okay, and this mat, if I need to add a material like say mat elastic one, I will just double click on it, and for this mat, the mat elastic property, okay, for the mat one from Ansys LS-DYNA is selected for this one. So you just need to feed this data, and this material can be used for the simulation. So if you see the unit system available, this is The unit system you can change from here. We have separate model tools also like OptiSlang, and also like I told you earlier, these are the connect tools supports for better optimization. Now in LS-DYNA, if you see, we have seen the engineering data which I have already created here. These are the different cells. The same data I can duplicate, the same data I can transfer from one cell to another cell. Okay, so if I want to duplicate or if I want to transfer the data, I can replace with another uh, uh, like another software, or like say not software, we can say another uh, solution or another solver. Okay, so if I want to go with explicit dynamics, so which is an autodyne tool which is running at the back end, we can use it that. But it again, the pre-processing generally, the meshing things, it depends. It will create. It can use the same mesh because it is an explicit technique only. But when you try to change the explicit formulation or explicit analysis to any other simulation, like say modal analysis, okay, like say static structure. So the thing is, the mesh elements are redefined, okay, but you need to check for which uh, like which mesh you are using. Are you using a linear mesh or quadratic mesh? So, like in static simulation, generally we perform or we use quadratic mesh technique. Okay, so like say second order elements are being used, but in explicit, generally we have to go with uh, like say first order, that is uh, linear elements. So those things we need to keep in mind while creating a duplication or transferring the data. Now, this is the model. If you see, this is a simple model of PCB. Okay, and in this, I have defined like mostly starting with defining the unit system. So here also I can define the unit system, which unit system I'm going to use. So if I'm going to use KGM, okay, like say, so LS-DYNA has its own like say unit system. So unit system in LS-DYNA is consistent. Okay, so if you define those things earlier or in the control card also, uh, it is we can say it is very mandatory because control cards will generally play a major role to well, like say unit plays a major role to define the quantitative factors or the property factors of a certain model, okay, of a model or of a component. So the weight and those things generally depends upon your unit system. So unit system is very much important when coming to a strength part or stiffness part or mass factors, okay, or even for the boundary condition. So we have transferred the this circuit model basically. If you see this circuit, if this one is the shell model, this one the solid one. Okay. So what we have did, we have created certain heat sinks are there. Okay. These are memory, CPU, and PCB, which is this one. This one is created in a shell format because when we create to we can say to reduce the computational time, generally we have to do this kind of techniques. So this is a hybrid technique we can say, okay, where we have used shell and solid model both. So just refer this one, you can see the gaps, but these are not the gaps. The thickness has been considered here. Okay, when we consider any mid surfaces, generally we need to define those factors. Okay, and we have created certain materials. So materials like PCB, you can see here also. Okay, so material we have created, these are like the plastic failure point factors we can define. This thing is generally defined in workbench engineering itself here. So when you define a PCB material also, you can see the plastic strain failures. So it tells you at what after what point the failure will be considered. Okay. Aluminium is there. So aluminium, PCB, and structural steel. These things have been considered. Like this structural steel is the default material. If you don't define any material in workbench, it will automatically define structural steel. Now these are like the separate COM coordinates defined for this one. Okay, on the battery. So if you can there easily select and insert and define the coordinate systems. These are the connections. You can see contacts. Now the contact techniques are very different here. So if you see the contacts, we have defined bonded contact. We define the behavior also, but bonded contact in this sense, uh, it automatically get transferred to tied contacts in this. When you transfer the data, okay, it will automatically get transferred. Now all these contacts, if you see here, this one is defined in bonded. And you can see the body interaction we have separate because this is a kind of a single surface contact which is generally created by uh, Ansys workbench automatically. This is the mesh defined. You can define the element orders, which is considered as linear. But by default, when you select LS-DYNA, it will automatically take into linear. We have defined the drop height here. Okay, so drop height is defined, and we have created a rigid wall. So all these parameters, if you see in right click on LS-DYNA, you can insert those all parameters like say part, condition is there, rigid body tools. If you have a battery, circuit short, resistance, battery thermal abuse, trackers, okay. So if you have any external loads, if you want to import, you can import from here. Okay, not only that, if you want to see certain add-ons, so you can have the add-ons here, but which is for the explicit approach. So if you want to give a keyword manager, you can use a keyword manager. It generally gives you the flexibility to check the keywords of LS-DYNA. Okay, and these are like the techniques you can see here. So if you see automation, your other automations can be used. Learning and supportive and this innovation space, you just need to click on this options and it will redirect, the software will redirect you to the particular location. LS pre-post, these are the techniques which are generally used in the LS pre-post. These are automatically, you can just click on it and it will be used for your application. Now, when we go to the bonded contact, okay, I will just show you about drop height. We have considered here that 1 meter at Z direction. We have created a rigid wall which is being created here. So we have defined the COM where how the impact should be happen with respect to the coordinate system. Okay, the gap is defined, the offset is defined, mesh plus gap. Okay, and we have solved this solution. Okay, uh, here you can see the most important part is the analysis setting. So end time is generally the simulation end time we need to define at what time we need to stop our simulation. Now when you see this one, this is basically the impact of the circuit board where you can check the stresses and all. Let me remove this one. So this you can do transfers. See like this. This one is in Pascal, okay? So with the help of this one, you can identify what is the peak stress, okay? Now observe this thing here only. So if you want to go with different views, multiple views, you can do with different uh, like say managing for different seconds. Okay, so for each time step or for each time you can plot the plots. Mm. And similarly you can measure the acceleration. What is the total acceleration developed? There are certain user defines also like say effective plastic strain. What is the effective plastic strain developed on the model? Okay, after an impact, there is no effective plastic strain. So this is just a kind of a simulation which will give you an idea, okay, how the simulation or when we define uh, the loading conditions, okay, for a certain, uh, like say for certain directly use element formulation, okay. So what will be the output? So in ANSYS settings, you can see the output definitions which we need to define, okay, like say at what space points, how much space points need to be tracked, okay. So this definition is important. Time history output is needed, okay. I just want to identify or I just want the wall forces, so I will create those things here or set those things there and then run it. Now the same simulation if I use with certain element formulations, okay. So what happens basically now, the results what we are getting in this case we can revalidate, okay. So we can check uh, the solver output also. So how we have to check it? In solution generally we can check the energy summaries, okay. So when the solution completes with a normal temp termination, generally you can change the solution information to report energy summary plot. So there is an increasing hourglass energy coupled with increased oscillation within the system and increasing the kinetic energy, indicating possible problems with the solution. This one. So now further we can do what things. So if you have this kind of scenario, by default, LS-DYNA software uses the under integrated elements. Oh, so what under integrated elements you can see? If you want to check those things, either you can go with the summary here and check for the solver output and you can look for those. So you just need to go to the solver file directory and in directory you can look for glstat, okay, or even you can look for .k files. So when you have a .k input, okay, this is .k input, and if I import this .k file, just select this thing to .k, and I'm going to open this same file, the same input deck, which LS-DYNA used for the simulation, where we are having some issues with summaries and all. So here you can see this is LS pre-post, and it will tell you about what sort of uh, element formulations we have used in keyword manager. So you can directly open also in notepad and look for those things. But if you go with here with the section part, in shell section you will see it by default it has used element formulation 1, sorry, element formulation 2 here for shell, because by default it uses 2, and for solid it has used element formulation 1. Just a second, take some time to open. So this is element formulation 1. So these are the element formulations available which we can use for solid elements and shell elements, and this happens in uh, when you directly start with the mesh or create the uh, like say uh, directly with the workbench you have created the data and by default the solver has taken the inputs, okay. So these are like the bin out tracker also. So this is bin out means this is the contact tracker, okay. Now when we go with other solution where I have updated the sections. Now in this we have option for parts. So in part we can go with section. So when we click on section, we can create or select the formulation. So we have selected fully integrated, that is 16 for shell, and for section 2 we have selected -1, which is a fully integrated solid. Now in this case, what happens when we use this element formulation? Okay, so the results can be better captured by using 3 integration points. Okay, now one of the thing is creating an integration point. Okay, so when we have a poor aspect ratios, we can say, or like say reduce integration, we generally the result tracking is not up to the mark. Okay, so with this case we generally created this sections, okay, and solve it. Now, if you see the difference in the summaries here, okay, now the fully integrated shell, this one is the fully integrated, and this one is, if you track these two energy summaries. Now you can see this summary, and this is the difference between the other summary. Okay, now when we compare the system A, previously system A with system B, okay, this one with sections defined, okay. So the fully integrated shell and solid elements have eliminated the hourglass energy. So this is the hourglass energy you can see, and here also you can see the hourglass energy. Okay, so in this case, the hourglass energy is totally eliminated. Okay, for the system B, and now the loss of kinetic energy is corrected and accounted for internal energy in the system. Okay, so these things like energy summary plots are very much important. So you need to identify what sort of element formulations we are going to use, whether these are appropriate or not. You need to monitor the hourglass energies, the contact energies. Okay, so these things similarly when we create the model directly with LS-DYNA. Okay, like in pre-post, the thing is like we just need to if you create a model in Workbench also, you can have option directly from the solutions here, and in the solution you can write the input file directly. So you can write a .k file, and that .k file you can import in ls pre-post, and the same file which you have imported or exported, you can run it. You see in mechanical Workbench, generally here in LS-DYNA Workbench, you can run the solution here itself. Okay, so you have option to solve it here only. Okay, but in ls pre-post, we do have options to go with explore options. Okay, and like say moreover with respect to applications, uh, but we have to use ls run to run the deck. So ls run is there, which is been used. So ls run, you can see the option here, and you just need to select the file, this .k file, and you just need to drag and drop that file here. And this file you can run with, say, like say how many number of cores you have to run, what memory you have to set, whether you have to run with single precision, double precision, based on your licensing. Okay, and you can run the simulation. So when you run the simulation, it will give you the same output which I have got in mechanical here. This one, just a second. This solver output. Okay, so if I run this one, This one only will this uh, ls run will open that file. Okay, you can see this files. So you can run directly and under command prompt you can see uh, this is the same output which is coming here. Okay, well, this is generally we can say a kind of a overview session which we had today. But if you want to go more in depth, you can visit these websites where you will find out more over tutorials, what is the version history, links, example models, conference papers. Okay, link to certain models where tire models, dummy models are available. Okay, and you can refer like say ALH also if you have if you go with ALH approach. Generally in ALH you will have more detailed information available on solving the respective problems or with respect to domains. Okay, so in the summary we can say uh, this today's discussion, whatever we had on LS-DYNA, is mainly uh, to understand what is the strength of LS-DYNA. Okay, how LS-DYNA is used in the industry, and it is one of the most powerful tool for solving nonlinear dynamic multiphysics problem. It helps to teams to master complex designs. You can accelerate, simulate, or uh, you can accelerate the simulation, sorry, and handle massive load models. Okay, so if you have large models having thousands of components, okay, you can easily handle by Ansys LS-DYNA. um, you can see how it achieves the real world accuracy because there are comparison studies of impact problems on LS-DYNA and real impact simulations, whether it may be automotive, aerospace, manufacturing, or biomedical or civil engineering. LS-DYNA delivers confidence through high fidelity virtual testing. Okay, so with this, we can just wrap up the session. But if you have any queries, any questions, you can ask me.